All right, here we are. This time talking about two of the things we have just been discussing. One is torque and the lever. So we're going to take the idea of torque and apply it to a lever so that we can solve questions or problems that involve levers and torques. So just to remind you, torque is equal to a force applied perpendicular to the distance. And of course, if we draw ourselves a couple of pictures here, if we have a big long board, and the board is sort of balanced here at this point, okay, so we can say that this is the ground down here underneath, and we have this large rock here that we're trying to move or something. Then what we do is we apply a force of pushing or pulling. I'll draw it this way, pushing straight down, right? And what that would do is that would create a torque. And the torque would be, we would have to figure out the distance to the fulcrum, which is the R, right? So there's our R, and the blue arrow is the force. And notice that the force is perpendicular to the R. And of course, we also have learned about levers and the different classes of levers. I want to put some more words on here. This is a force in blue, right? And we sometimes call this the effort force, because it's the one that you have to push to make the rock move. You are making the effort. So that's called the effort force. And then this would be the effort arm. This long part here to the fulcrum, the effort arm. And the other part of the lever on the other side would have what we call the load. Now there's a weight or a force of gravity pulling one here. Now it's a little bit angled here because of our picture, but we're going to just assume that we're going to use the perpendicular component of that weight. And that's the force here. And this is called the load force, the weight of the rock. And if we look up here, the distance from here to here, which is the R, well, it's a different R. What we could do is we could put an R with a little L beside it, and on the other one, we'll put a little E beside it, effort arm. This would be the length of the load arm. So when we start talking about our levers and how we do torque on them, we'll use these terms. All right, so basically, if we just write a little, I'll put this back a bit, if we write a little expression here, let's just make a box, refer to that picture. What we can see is that the effort torque, caused by your pushing or pulling on the rod, on the lever, the effort torque is equal to the effort force multiplied by the length of the effort arm, or the distance from the fulcrum of the effort force. And we can also see that, if I move down a little bit here, the load torque, which is the torque where the rock is, the load torque equals the force caused by the load, which is usually their weight, but doesn't have to be. It could be anything. So it's the load force, multiplied by the load arm, or the distance. Oops, I put effort. Today's not a good day. The load arm, or the length of that distance from the load. Now, because it's like a teeter-totter, in order for you to do any kind of work or lift, there's a minimum amount of torque you have to create. Whatever the torque is that's being created here by the load, you have to match it over here with the effort. If you match it, you can create an equilibrium state where the teeter-totter wouldn't move at all, but it would just be at the point where it's about to begin to move. And so if you applied even just a hair more force, you could actually make the rock lift or move the rock. So what we're doing is we're comparing the effort torque and the load torque on a particular object. And so what you have to remember is that we're always looking for the effort torque to sort of balance out the load torque, or to equal the load torque when we use a lever. This is what has to happen in order for you to be able to begin to lift the object on the end of the lever. And so if you look at our expressions, the torque of the effort equals the torque of the load, but we just finished describing how to calculate those up here. I'll go back. The effort torque is the force that you apply at the effort spot multiplied by the length of the effort arm, or how far you are away from the fulcrum. And the load torque would be the force caused by the load. Often it's the weight or the gravity of the load, multiplied by RL, which is the length of the load arm, or how far you are from the fulcrum on that side of the lever. And really, that's all there is to it. So let's see if we can use this little bit of information right here to solve a couple of problems together. All right, we'll just move down here. Let's take a simple problem. Let's say that a camper is trying to move a rock. And so we'll use our lever here. And we'll put a fulcrum here that it's balanced on. And we'll put a big, large rock here. He's got the lever sort of underneath it. Okay. Actually, what would more likely be the case is the rock would be kind of sort of like this on the ground, and the lever would be kind of tucked under it so that we could push the rock. All right. So let's see. Let's get ourselves some information. So the effort force that you're going to push with, the effort force is this way, pushing on the lever, F, effort, is equal to, let's go 450 newtons of force. Okay? And the length of the effort arm, the distance from this effort force to the fulcrum, so that would be R effort, the effort arm, just think of R and arm, that's going to be about 2.2 meters, let's say. Nice long stick you're using here. Okay. How much effort torque is being produced? If this was you pushing on this rock, how much effort torque are you making? Well, the effort torque is equal to the effort force times the length of the effort arm, right? And that force would be 450 newtons multiplied by 2.2 meters. And the answer then would be about 990-ish meters. I think that's going to be close. Not meters, sorry. Not meters. Newton meters torque. We found the torque, and the unit must be Newton meters of torque. Okay? So I'm just going to double check that that worked out. Yeah, looks good. Okay, so that's an easy one. That's not very difficult at all. And of course, we could have done the same thing for the load over here by the rock, but the question hasn't given us any information about that rock, so we can't figure out anything else like that. But here's something that we can figure out. We'll get a little more information. Here's another example. All right. Let's say you have a trailer And your trailer, it's the end of the season. There's the back end of your trailer, your camper. And you want to put it up on blocks for the winter because you don't want the wheels to get all flattened out from the weight over the winter. So you devise a lever. So let me put the ground in here. There's the ground. So what you do is you build a lever by putting a sort of a little fulcrum thing to balance here, maybe a log or something, and you stick your piece of wood under here like this, and you balance it on the log. So I'll color that all in. There's the piece of wood that you're going to use under the bumper, or under the, I guess you wouldn't use the bumper, would you? You'd probably find a nice solid part of the frame of the trailer to lift from. And you're going to lift up. Okay? So, the trailer is the load, and the effort is you pushing. So, let's give ourselves some information here. We're going to push with an effort force down here. With an effort force, let's see. I don't know what we'll do. We'll figure out what force we need to lift the trailer. But we're going to need some more information. All right? The load force, which is the weight of the trailer pushing down like this, the force of the load, is very heavy. It's going to be 1800 newtons. 1800 newtons. And the distance of the load force, RL, the length of the load arm, we're going to say is 0.45. Right? And I'm going to tell you that the length of the rest of this rod, so the length of the effort arm, let's say it's a 3-meter rod, so the length of that is going to be 2.55 meters. And I would like you to figure out for me what the load force would have to be in order to lift this trailer. Well, in order to lift, remember what we said, the effort torque must equal the load torque. Okay? And of course, these formulas, we are looking at just the magnitude, just how much of the torque there is. We didn't really discuss which way it's going to move, but we know that it's either going to be clockwise or counterclockwise, right? So we can tell the way it's going to move from the picture. All right. Effort force times the length of the effort arm goes here, because that's what the effort torque is equal to. And the load torque is equal to the force at the load times the load arm, or the length to the fulcrum. And we have some of these numbers. We have an effort force. Well, no, we have an effort force, it's a question mark. But we have the length of the effort arm right here, 2.55 meters. So we can put 2.55 here where it says effort arm, RE, the R distance. We also know the load force. It's the weight of the trailer, it's 1800 newtons. So we can put that there. And then the effort distance, oh, look what I did. I did it again. I'm so sorry about that. You're probably all thinking, what the heck? It's the end of the day and I guess I'm ready for a nap. That's the load arm, isn't it? Not the effort. And it's, of course, this number right here. So it goes 0.45. There. I'm pretty sure we have it right now. So now let's do some math. What we have to do to solve this is first we have to multiply 1800 times 0.45. So this side turns into 810. And then over here, if we divide both sides by 2.55, we get FE equals 317.6 newtons of force. Well, that's how hard you would have to pull down or push down on this end, the effort end of the lever right here, in order to lift this heavy trailer. Okay? So there's another example of how this might work. Okay, great. Now, whoops, I keep moving myself down here. Let's go back down to the bottom. Okay. All right, and so we'll do one more example. There we are. Just to show you that sometimes it doesn't necessarily have to be an actual effort force. I'll just show you what it could look like. Sometimes, if you're talking about two things on a teeter-totter that are balancing, say there's a balance here, well, you could have an object here and another object over here. And nobody's really pushing, but if you want it to balance, the torques, let's call this object A and call this object B, then the torque of object A has to equal the torque of object B, at least in magnitude. Obviously, B has a force here that's going to be pulling it down, and A has weight as well. But notice what happens. B tries to make it go this way, which we'd say is clockwise, but A is trying to make it go this way, which is counterclockwise. So these two are working against each other. So what we say in math is that the magnitude of them is the same. That's what this is all about. But their directions are opposite. Now, which one is force and which one is effort? Well, and which one is load? Well, it doesn't really matter. You can name one the force and one the effort, and then you can work it out the same way. So instead of actually somebody pushing, maybe it's just a weight here that we've used. So you could call this the effort, and you could call this the load. And then the force would be, this would be the effort force. Sorry, the load. Call that the load. This would be the load force, and this would be the effort force here. And to be honest, it doesn't matter. You could even reverse it. So sometimes it's just, I wanted to point out that you might have a situation where you're not actually pushing or pulling, but it's just two weights on a teeter-totter, on a lever, with a fulcrum somewhere. The fulcrum might be here, but it might be in the middle, could be over here, it depends. Right? And these little rules that these rules we've done, they work for all classes of levers. So even though you have a class 1 or class 2 or class 3, it doesn't matter, all classes of levers. The example we did was a class 1, but it works for all classes of levers. All right, so having said that, you can move on to the assignment, which is a couple of practice questions that involve using torque and levers to try to figure out things about the effort force and the load force and the arm lengths.